Hello everyone. The paper we're discussing today is Domain Isolation in FPGA Accelerated Cloud and Data Center Applications. Cloud computing and data center applications utilize integrated circuits. They have improved performance than traditional processing cores such as CPUs and GPUs. There are two common integrated circuits, ASIC and FPGA. ASIC, or Application-Specific Integrated Circuits, are hardwired from the factory. They don't provide any reprogrammability without physically manipulating the hardware. And ASIC chips only serves one function or application. They're very efficient while being cheap to manufacture. FPGA, or Field Programmable Gate Arrays, provide a more versatile use case by allowing their circuits to be changed on demand using hardware description language. Therefore, FPGAs can be reused and upgraded for different applications, and they still provide a significant performance boost and cost reduction than traditional CPUs and GPUs. The idea of using FPGA chips to improve performance and cost is still recent, so there are areas to improve. First, FPGA chips are often not utilized to their full potential when executing a single instance of an application. So how do we solve this? A common strategy is to have FPGA space shared by multiple instances to utilize waste resources. However, space sharing the same chips could present security issues, and those issues would be the focus of this presentation. We will first go through a generic but vulnerable cloud structure. On top, users would access virtual machine instances to execute applications and commands. Those applications will be processed by a virtual machine manager that will allocate a virtual region in the FPGA space to increase the performance of the application. Each virtual region contains an accelerator, which is responsible for computing data with FPGA circuits. Virtual regions would also hold buffer data for computations and the results. We consider two possible scenarios where the confidentiality, integrity, and availability of an application are compromised. In scenario 1, as seen in the left figure, an application accesses the virtual machine region of another virtual machine instance. The attacker can then steal or tamper data of the victim, which could prevent the application from executing. In scenario 2, as seen in the right figure, we consider the attacker has gained full access to the virtual machine manager. The attacker can then run malicious software with superuser privileges and access the entire address space. The attacker could gain data access, block user traffic to the FPGA space, and utilize the entire chip for their own applications. To improve on the base structure, the paper proposed adding additional security entities. An additional security server is deployed. The server is responsible for granting access sessions from the application to the FPGA accelerator. The server coordinates with HMAC to supervise the security usage of the FPGA space. HMAC, or Hardware Mandatory Access Controller, is mainly responsible to only allow permitted access to the specific virtual regions. It does so by using session information generated with the security server. Only when an application can provide the correct session information, then it will be granted usage of the appropriate virtual region. Essentially, communication between software and hardware accelerator is encrypted and checked against the session ID. Here is the sequence diagram of the security protocol. Initially, an application requests the usage of a FPGA space by sending its information to the security server. Then, the security server will inform the virtual machine manager to allocate appropriate FPGA space for usage. Following this, the security server generates a random session ID and requests HMAC to generate its key. When that's done, the session information is forwarded to the application, and you can start utilizing the accelerator. The application will send packets, including the space of access, the encrypted message, and the encrypted session ID. All traffic will go through HMAC first to determine its authenticity. If the HMAC detects that the decrypted session ID matches with the session ID of the FPGA space, then the command is successfully executed. However, if there is a mismatch, HMAC will acknowledge a potential security breach, and the cloud provider can decide the mitigation procedure. In this slide, we present a case study where the security structure is deployed in a real-life scenario. We program the VR with a JPEG encoder. It takes a 32-bit value as input and returns a 32-bit JPEG stream. In this scenario, the attacker has already gained access to the virtual machine manager. They can therefore access the FPGA space of the victim. However, the attacker does not have the correct session ID and session key. As a result, only the read and write request from VM1 is accepted by the HMAC. The requests sent from VM2 and the VMM are discarded. There are two matrices to measure the overhead. First, the initial generation of the session takes time. Secondly, the continuous decryption of session ID by the HMAC takes FPGA resources. Simulation of the security structure shows minimal overhead in both matrices. However, in a real-world implementation of a JPEG accelerator, the overhead is more obvious. Overall, the security feature contributes to a reasonable overhead while providing valuable improvements to the system's confidentiality, integrity, and availability. Thank you for listening to my presentation. Have a nice day.